Yes, welcome back. So in the previous topic, we were discussing about the when we discussed about the Euler's theory. We have discussed for the long columns, short columns. What are the assumptions has to be considered whenever we having a different conditions, like both conditions are fixed, or in a both conditions are hinged, or one end fixed and other end free. So we have all discussed that is about in the previous topic. So now we're going to discuss or we're going to derive that Euler's critical load for an long columns. In that, one of the condition is when the Euler's critical load when the both the ends are hinged. So hinged is nothing but when the both the ends they will be having a support. And yesterday we have discussed how the columns will get failure because of the buckling, how the buckling will come into the picture. So all those things we have discussed. Now we are going to consider for the long column. This is also one of the long column where the condition is both the ends are been hinged. Hinged, that is what we have discussed in the previous topic, is how the hinged is nothing but having in a both the end the support. You can able to see the diagram in this, both the ends having some support, and both the ends it is having an axial compressive force that is acting on the column. There you can able to see this column, and this is what happens whenever we are going to apply the load. That is what we are going to get in a deflection. So the deflection what we are going to measure, that is what we call it as an a y. And the deflection, what the deflection is occurring, that is what we call it as a buckling. So now based on this consideration, by using this both the ends are injured conditions, we're going to derive an Euler's critical load for this both the ends injured. By considering a long column with the both the ends are injured is subjected to having that critical load. That critical load P is acting on the both the ends as shown in this particular diagram. Now what we're going to do is will consider that section at a distance x from the origin. Let y be the deflection. This y is nothing but the deflection. The deflection is nothing but where the buckling is taking or the deviation is getting from the column. Let y be the deflection of the column at this section. A bending moment in terms of load. Again we're going to consider the deflection. The deflection can be calculated in nothing but in the form of bending moment. So we cannot able to measure. By using that bending moment in terms of the load, we can able to identify that deflection. Y is nothing but a change of position because of the load applied. The deviation or the buckling has been taken place. That is the deflection y is given by m. M is nothing but a moment, and where the load is p is nothing but a load, and y is nothing but a deflection, right? So this is what we can able to write down this when we consider from one section. And now what we can able to do is we can also write that for the beams or in a columns, the bending moment, what the bending moment or what the deflection is coming proportional to the curvature of that beam. Even that the bending moment is also equal to the curvature of that beam, which for small deflection can be expressed, which the small deflections can be expressed as where E will be equal to the Young's modulus for that particular curvature of the beam, and I is nothing but a moment of inertia. This is how we can able to write the beams for an columns even when the bending moment is proportional to the curvature of the beam. So what we can able to write that P and Y, the load and deflection. So instead of bending moment, when we want to consider that curvature also, radius of curvature for that beam is E into I, that is Young's modulus into I. We're going to differentiate with respect to d square y by and d square y by dx square. Or we can able to write down this equation by sending this term that side is d square y by dx square. By sending this negative, it will become positive, that is p into e by I into with respect to I or with respect to y, that will be 0. This is where we can able to rewrite this equation. Now what happens when you considering that equation? Thus there is a this is a second order differential. This is what the equation second order differential equation, which has in a general solution from form of, this is a general solution form for the second order differential equation for what we are considered for in a long columns, where y will be equal to c1 into sine into pi into root of p by e into I plus c2 into cos x into root of p by e into I. This is what, where c1 and c2 are the constant values, and as we know that p is in a critical load and e is in a modulus Young's modulus, I is nothing but a moment of inertia, where this y is nothing but a deflection. So this is the standard equation or a standard differential second order differential equation, which is having a general solution form, that is y is will be equal to c1, the formula what we have got, where c1 and c2 are the constant. The values of constants can be, see now we don't know the values, c1 and c2 are constant. So the values of constants can be obtained by applying the boundary condition. By applying the boundary conditions to this second order differential equation, we can able to obtain the values. So first we're going to see y will be equal to 0, and even at x also will be 0. That is a deflection of the column, where that is the deflection of the column must be 0 at each end. Both the ends it will be 0 when at the condition is y will be equal to 0 and x is equal to 0, and it is both having a support at the each end. And applying these conditions by putting these values in these equations, so giving us this by equating this by applying these values in this equation 3, what we got is now for y to be 0 and x2 will be equal to 0, then the value for c2 must be 0, since because if I multiply with the cos since the cos 0 will be equal to 1. Now I'm getting the value here 1 because the cos value is having a 1. By substituting y equal to 0, now what happens, the y value will be 0 only, but the x what we're going to is, now I'm going to replace that x will be equal to the length, which is the length of the column which is having. Now I'm going to replace with the x with the equal to x will be equal to length. Now from the equation what we can able to write is, so now the y value will be equal to 0 and the x value, now what is, I am going to replace with that x will be equal to 0, c1 into sine, that is I'm going to replace x with the term of L. Now the x value will become an L. Now root of p by e into L, with respect to x I am replaced with the L, while for y to be 0 at x will be equal to L. Now the y value will be 0 and the x value will be equal to L. Then while substituting that, c1 will become a 0 because there is no equation at all. If the c1 and c1 and c2 both are 0, then what happens if the c1 both the constants values are 0? Now what I am going to write down is c1 is 0. What the c2 I am going to replace it, because the c1 and c2 are 0, I am going to just write down the sin L into root of p, it will be equal to 0. This is what I am going to get the when substituting this applying the boundary conditions. So what happens when applying this equation, which results in fact that L will be equal to root of p into e by I, where that will be equal to n into pi. N is nothing but 0, 1, 2, 3, where we are going to give the infinity value, or we can able to write down that value as L will be equal to root of L into root of p by ei. E is nothing but critical load and E is nothing but an modulus of elasticity, Young's modulus, and I is nothing but moment of inertia, where n is nothing but numbers, different numbers or different points where it can able to extend. So I'm going to write or replace this equation, or you can able to rewrite this equation. Yes, by rewriting that equation, what are we can able to write down this, by taking a critical load outside, where n square into pi square into e into I by L square. Now first, whenever we're going to substitute that value, I'm going to take n will be the least value, from we're going to start from 1 to the infinity, so I'm going to consider the n will be having the 1. Now by taking the n value as a 1, by substituting that n value as a 1 in this equation, what we can able to write is nothing but p is nothing but a critical load will be equal to, I'm going to n value is 1, 1 square will be 1, so we are not going to write that n value, because we're taking the significant value of n is now, and the p what we're going to write, the formula is p will be equal to pi square into E is nothing but Young's modulus, where I is nothing but a moment of inertia, where L is nothing but a length. So what we can able to write now, the standard equation for the both the Euler's critical load for when the condition is both the ends has been hinged. So the value is now p will be equal to pi square into E into I by L square, or PE we can able to write, or you can able to consider where L will be equal to LE, or also you can able to write down the LE, or you can able to write down the L square. So this is what the equation to find out the both the ends hinged. So we're going to use this Euler's equation for the when the condition is having an both the ends has been hinged. So the formula is p will be equal to pi square into ei by L square. So this is the standard equation what we can able to substitute the values to find out the buckling or any other given data to find. Based on this equation we can able to identify.